Hi everyone, time to go through the first midterm, give you an overview of some of the answers we were looking for and some feedback on how the midterm went. You'll find the slides that I'll be including here also available on the Canvas page, and of course be able to look at your grades in Gradescope and figure out what you want to do from there. As I said, in some of the discussion sessions at least, this is just to give you feedback more than to assess your overall abilities. So if you didn't do as well as you'd hope, now is a good time to think about it. I'm going to include a reflection exercise to help that process. And so I hope it provides the feedback for you to check in, make sure you're learning at the rate you want to be learning, getting control of this content to the extent you want to get the grade you want. That's really the purpose. The midterm is only worth 10% of the final grade, so again, there's no need to get too panicky at this point, but it is a good time to check in and see how you're doing and how that works with what your expectations are. So this first slide shows the results of this year's midterm compared to last year's. And you can see there's been a slight downward shift, a bit of a slip in the overall grades. It's not massive. The mean grades have dropped a little bit, the maximum marginally, but there are just fewer people in that upper category of the A's and especially the A's. A minuses are pretty strong, B pluses are very strong. So, and there's a few of you down at the lower end who really do need to pay attention and think hard about upping your commitment to the class and the time you spend on the class work. Again, the grade is only worth 10% of the final mark, so don't over stress about how important this result is, and use it as an indicator for going forward. So the true-false questions, we can get pretty detailed statistics from Gradescope, and you can see here is an overview of how people did on the true-false questions, and you can see overall there's lots of green. That's a good score. Overall, you see the fourth question was probably the trickiest one. We'll go through these pretty quickly. Each one of them, you can look at the slides on this, and the first one is about significant figures. I'll leave you to mostly read these and view them at your leisure, but here you can see the answer as we expected it, and the fact that 82% of you got this one correct. So this is a very strong result from everybody. In this question, there was some confusion about the effect of a non-compliant vessel, and some of you suspected there would be some kind of time delay between a pressure increase in the beginning or an increase in flow in the beginning leading to a flow out on the other end. And this really, in a perfect world, does have no delay. The instant new fluid comes in, fluid assumed being incompressible, there has to be fluid at the other end of the pipe that leaves. And so all these changes do indeed happen instantaneously. That's not the situation we're dealing with. We have compliant vessels, and so we have to take time into consideration and the compliance value, and things get significantly more complicated. The third one was really about non-Newtonian fluids. Most of you, I think, did fine with that and recognized that not all fluids in our body are Newtonian, so 84% of you got this one correct. And finally, this fourth one. This is one we did spend time in discussions, and it's kind of important as engineers that we understand what this question is all about. What I was trying to tap into here is our ability from a data plot, so from data we would collect in the lab, following a process that has a time dependence, from its beginning to something close to the end, or at least a significant time period, we can see in the graph we would plot from those data the initial value, the final value, and follow the time course along the way, and be able to use the fact that we're modeling this with an exponent even to define that threshold value that corresponds to 37% above the minimum value or 63% down from the maximum value. And that horizontal line will, which we can draw just based on those percentages, will cross our curve at some point. And if we drop vertically down from that crossing point, we get a very good estimate of the time constant for that system. And time constants, as we've said, are important characteristic values for a system. And this was one of the weakest scores in the true-false questions, and I really hope you review this, because this is engineering thinking that goes way, way beyond this class and in this type of situation where we're given data and asked to fit a function to estimate the behavior of that system and characterize it through one or more parameters that fit into that equation. And we'll be doing this again in the lab too, in the electrical context. So even if mechanical context is not clear, you're not that interested, this is pretty core fundamental engineering knowledge. So try and make sure you understand what we're trying to get at here. Now, the next two questions, or three questions, were all meant to be sort of longer essay questions. Problem 5 was about MATLAB, to test your MATLAB skills. And this is a pretty clear indication of the level of skills we expect you to have and develop through this semester. And you really need to understand this syntax. You'll get more of it next semester. You'll get a more detailed look at MATLAB, get into more of the features and functions, but this is pretty fundamental content, I would argue, and you should be able to handle all these things. We've gone over all of them in class, you've used them in homework assignments, some of them probably in the major project, and so that's a key piece that we're trying to tap into here. The last question on this page here is about the max function. We couldn't help but notice a lot of you ended up using the max function in a way that I have yet to find anyone in my circle of colleagues who would have ever guessed that the max function could be used with a 0 first argument in order to create a binary function, essentially replace the if statement in that homework assignment with something that may or may not be more efficient. It's certainly more opaque and harder to understand when you read the code. I would bet a lot of money that you got this all from some kind of large language model. That's not how we meant for you to use large language models in this class. We gave you an explicit if statement, said replace it with the new conditions of the problem and the homework, and expected to see that if function. We didn't downgrade you this time, but we will going forward. This is not how to learn coding. This is just not going to give you the knowledge you need to do well when you go to read somebody else's code, analyze code, figure out why yours isn't working, and you cannot trust a large language model to solve real-world problems yet. It will help you with pieces of it. It is a valuable tool, but at this stage, you just have to learn the fundamentals. You have to learn the basics. And anyone who used a max function in that homework, I would bet a lot of money, basically got that function from a large language model, probably ChatGPT or our wrapper for it, Copilot. And so the people who didn't get the max function question right here, which is a very simple function, or simple use of that function, don't understand the function, even though it's being used. It's part of the homework assignments you submitted. So please take this to heart and learn to do basic coding on your own and be able to work independently of these large language models. So again, the scores here were overall fine, but that one question I wanted to highlight because a number of you had problems with it. Now, problem 6 and 7, straight out of the homework type problems, simplified, I would argue, compared to some of the more challenging homework assignments. The message here is if you practice your homework assignments and make sure you can do them and understand every step, you'll do fine in a midterm. It's really that simple. And I won't go through the details here. The slides will give you all the information you need, how we look to have you lay that question out, what the numbers were that we were looking for you to get, and the kind of answers we were expecting. One thing I will add in the final part of this problem, and something I'd encourage you to broadly apply, is something I like to call a sanity check. So with time, you will learn to appreciate what are the sensible ranges of these values we're having you compute. What's a sensible range for a biological blood pressure, for example? We should have a sense of what that range is. Similarly, we should have a sense of what the size of molecules are expressed in Daltons. It's a very common notation used across chemistry. And so we should not be surprised to have megadaltons or kilodaltons. That is the very standard sort of size range, for proteins. And so that shouldn't be a surprise. If you get answers that are much more than that or substantially less than that, then you might want to be very careful. And I just encourage you to look at all the answers you get and say, does this make sense given my knowledge? I will add the majority of mistakes in this question, strangely enough, came about converting nanometers to centimeters. we got to get this under control. I mean, this came up during the exam. We just have to know these features of the system of units that we use every day in science and engineering. So please just memorize these if you have to, or use them enough so that you know what's going on. So the last question was, again, a classic example of compliant vessel with certain conditions, inflow, outflow, whatever. And most of you did actually quite well with this, 70–80% correct in general. There were some problems with some of the unit conversions here, some of the how to use the equations, how to use residual volume, but I would just go through that question with the help of the slides and make sure you understand what you didn't quite get if you had points docked for it. And finally, a few tips that I gathered up from the TAs and my own looking over the exams. This is a trivial one, but I know some of you traditionally work on your iPad, so you live in kind of this digital space. Your homeworks never see paper. That's fine, that's fantastic. But we have to learn how to scan documents. This is just a really fundamental skill. We're engineers, for heaven's sakes. Get a scanner app on your phone and get to know how to use it. A scanner app is not a camera. So what we wanted to see submitted were PDF files, not PDF files of images, but scanned PDF files. There's all kinds of instructions in the homework page for how to do this. There's half a dozen different free scanner apps out there. There's one built into the iPhone. Please just learn one of these things. This is just, and if you have problems, then of course ask us for help, but we're just not going to be accepting photographs anymore. You have to get around this minimal technical skill set to function in a conventional world today. In the true-false questions, we need something to work with in the context of an answer. So if you just pick true or false, you've given away the majority of the points of that question by not giving us some text, some explanation to work with. We try very hard to give you partial credit, even if you pick the incorrect true or false value, but we need some kind of explanation to get a sense you understand what the question was about and have some, at least partial sense of what an appropriate answer would be. As you've seen, proving something to be true is more difficult than proving something to be false. When it is a true statement, then you have to provide some augmentation, some additional information that shows you understand the question and can sustain or support the notion that the answer is actually true. Restating the question or the statement in the question is not really an adequate answer. That doesn't show any insight into the question. Schematic diagrams, we've discussed these many times. They're going to come up again and again throughout the rest of your engineering life, I would argue. And so just get comfortable with these, learn how to do them. Whenever you're not sure, just ask. I keep coming back to this. There are a whole team of people here ready to help you. And from tutors, TAs, me, Dr. Christensen, we're all here to help. So if you're getting stuck somewhere, please do that. We even have the TutorBot available that hopefully is also helpful for answering at least some of your questions. And just get used to the way that we're expecting you to solve these problems, the way we're expecting you to lay them out and to write the equations, all that stuff. This is just good, solid engineering practice. This is not just the weirdness of me or this course or whatever. These are just good, solid skills that will help you going forward. I hear this again and again from the seniors I talk to in interview, and they all realize the value that this convention, this adherence to a certain set of steps and process, the confidence that gives them, the improvement in the accuracy when they go to solve problems when they don't have the answers in front of them. Because after this course, you really will have to figure out answers and submit those answers with confidence. And so we have to develop the skills. It's really the whole point of this class. It is key at this stage and at the level of questions that we're giving you to address that you really do understand the details. This is not fundamentally complicated at the level we're presenting it. All these concepts can be much more complicated. We see that sometimes in the discussion sections, but I try and keep it at a level of complexity, and my expectations are such that you really should understand the details. So if there's something in the textbook or something in a discussion note or something you come across in the context of the course that doesn't make sense to you, then you just need to ask and dig into it and figure it out. Use whatever tools you can, talk to each other about it. Explaining it to each other can be incredibly helpful and powerful for everybody involved. Those doing the explaining learn it even better through the act of explaining. So just make sure you get to the level of detail that we provide in the textbook, in the materials. And you'll do fine in terms of assessment, but you'll also get used to this hard work that is involved in understanding the details of something. But that just comes with the territory. You cannot do well in this engineering world unless you're willing to engage to a certain level of detail. Try and keep up. I mean, this sounds so trivial. You've heard this a million times before, but try really hard to manage your time, balance your time, so that you're not falling behind. The worst thing is to fall behind, because once you fall a little behind, then the next week makes you fall further behind because you didn't get something from the week before. This course builds from week to week, especially sort of block-wise. So you could argue, okay, we're done with mechanics now, so I can forget all that stuff. Well, you can't, because we have a comprehensive final exam that will go back and pull some questions from that earlier part of the semester. So even as we move forward into electrical aspects, make sure you have the elements of this midterm, the content that went into this midterm, make sure you have this under control. And then finally, the MATLAB section of things and our MATLAB use generally. This is just the first of the computer languages you're going to learn going forward. I mean, this is how engineering works these days. So learning good, habits now will again be really valuable as you go forward, literally into the next semester, where you have a whole course on MATLAB. So be as precise and careful as you can, because computers are remarkably stupid. Fundamentally, they do very low-level operations, and everything is built on top of that. And you can be fooled, especially when you deal with a large language model, into thinking that computers are incredibly smart and they can read my mind and know what I want to do next. That's not fundamentally how they work. And so when you go to program them, you have to be the one in control. You have to be sure you know what every single character in that line of code is doing. The semicolon in MATLAB is a great example of without you get dramatically different outputs. And we should just learn that level of care and detail checking, because that's the key to success in programming. I think that's enough for now. If you have questions, please don't hesitate to get back to us. I'll give you a couple of days to mull all this over, look through the questions, look through the slides, look through this video, and then we'll open up the possibility for some regrade requests. Again, these are regrades where you see a clear error. We've clearly missed something. The caveat is there. If we regrade, and we may have missed something. We may have even missed an error in your first try. So if you open up that door for regrading, then we will jump in and do a very careful regrade to make sure that you get the full credit you deserve. But in that process, we can't promise we won't find additional mistakes that we might have missed the first time through. So always keep that in mind with these regrade requests. Sometimes it's sort of less expensive, less risky. Just come talk to us and ask us to explain something. And we're happy to do that. Just reach out, make the time, and we'll try and do our best to be available for you. Okay, that's enough. Hope that was helpful, and look forward to the rest of the semester and continuing to grow and learn and hopefully have at least a little bit of fun together. All right, thanks so much for your attention. Take care, and we'll see you soon. Bye for now.